Hello my dear students, this is Nikhil. In this class we will try to understand about choppers, which is a very interesting, or I can say best innovation in the field of power electronics, that is a chopper. As you know, chopper is that circuit or that device of power electronics based on power electronic switches which converts a DC into a DC supply, or basically it is a circuit which actually enables us to have control on DC power flow. That means you are not going to alter the DC power flow. The power is flowing from one direction to other direction. The only thing that you are doing is you are placing a chopper in between this DC power flow and you are trying to regulate the DC power flow. Or in other words, I can say chopper is also called as a switched mode regulator. It is also called as a switched mode regulator because by using of power electronic switches, you are regulating the DC power flow in a particular transmission line or in any network for that matter. So before actually understanding properly the functioning of a DC-DC converter or a chopper, there is one important aspect that we have to study, that is the behavior of inductors and capacitors. See, actually my intention was to explain about this question which was asked in GATE 2015. So before actually getting down into this chopper operation, I want to explain some important fundamental principles that govern the operation of a chopper, because once you are strong with these fundamentals, and I also think the things which I am going to explain now you rarely find even in the YouTube. So please pay attention and listen properly. As you see here is a chopper, like I am telling you. This chopper is basically a step down chopper, what we call. Step down chopper means it is a chopper which will reduce the DC voltage. Output voltage will be less than the input voltage. That is called as a step down chopper, like a step down transformer we have in AC circuits. Similarly, a chopper may also be a step up. That is called as a step up chopper, and it is also called as a boost chopper. Whereas a step down chopper is called as a buck chopper. So these are some basic things which you already know. Because this is ours is like a crash course, we are mainly interested in discussing only such things where you find rare explanation and the things which are very crucial for our understanding regarding this particular topic. If you look at this particular chopper, you primarily see there are two important things, that is inductor and capacitor. You cannot basically create a good functioning chopper without presence of an inductor and capacitor. They are very much essential. The reason is because you are using a switch, and as the name itself says, it is a chopper. Chopper means you are cutting. That means whatever is the input, whatever is the power, so whatever is the current or voltages that are coming in this DC power flow are being chopped by this particular switch. So when you are chopping a current or voltage, what happens? So there is a chance of harmonics entering into the system. Once harmonics come into the system, the performance of the load, the performance of the system, everything will smash down. So in order to regulate the harmonics or the effect of harmonics, and in order to make the DC power flow smooth, we require a filtering circuit which is L and C. L and C basically forms what is called as a low pass filter. So this combination of L and C forms a low pass filter because this is a DC to DC converter, or I can say DC power flow regulator. You have to allow only DC component of the power but not AC component which is an harmonic. So you have to use a low pass filter which will always accept DC power flow. So it is very much important for us to understand the behavior of L and C in a circuit. So let us see how an inductor behaves first. So here I am having an inductor which is having some inductance L, and this is terminal A and this is terminal B. So what is the behavior of an inductor basically? Inductor is such device when you are passing current through the inductor. What does this inductor do? It will convert this electrical energy into magnetic energy, or I can say it will produce a magnetic flux around it and it will store the energy. Isn't it? It will store the energy. So it is storing energy by utilizing which component? By using the current. By utilizing the current. So any storage element in the world will not accept sudden changes in the energy that it has stored. Isn't it? This thing we are very much aware because we are the students of physics. Any system has got some inertia and it does not allow the changes in energy through the system. So likewise, you are having the magnetic energy which is due to the flow of current. This inductor does not allow the changes in current. If the current changes, the energy stored will change. Isn't it? The energy stored by an inductor is given by half L into I square. So when current through the inductor is changing, then it will induce a voltage opposite to the supply voltage called as VL, and it will be proportional to the changes in the inductor current. So this is the relation that describes the voltage and current relation in a inductor. So I will take a circuit and try to further explain this. So here is that circuit. Let us say I am placing the switch at position number 1. When I am placing the switch in the position number 1, what is happening? This VDC source is connected to the inductor, and inductor starts building up the magnetic flux, or it starts accepting the current. I can write down under that condition the applied VDC will be equal to the voltage across the inductor, isn't it? That will be equal to L into di by dt. If I want to find out what is the value of that current going into the inductor under this condition, IL will be equal to 1 by L integration 0 to T1 VDC into dt. T1 is the time for which I am closing the switch at position number 1, or I am placing the switch in the position number 1. Since VDC is a constant, then IL will come out to be. So if I simultaneously try to plot the waveforms here up to 0 to time T1, I am applying some voltage across the inductor that is equal to how much? VDC voltage I am applying. But on the same time duration up to 0 to T1, how the current is? VDC by L into T1. That means this represents a ramp signal, positive ramp, isn't it? So the current value is increasing up to how much time? Up to T1 time, the current is increasing. So after T1, what I am going to do is, immediately I am going to change the position to switch number 2. What I am going to do? I am going to change the position to switch number 2. Now this is switch number 2. So when you are placing the switch to the switch number 2, what is the voltage that is connected across the inductor? Minus VDC is connected. So if you perform the same type of analysis, then I will get the current through the inductor will be minus VDC by L. Let us, I will place that switch for some time T2. This will be the current through the inductor when the switch is placed in the second position. That means what does it indicate? It indicates that the direction of current flow has been changed. The direction of current flow has been changed. If the direction across the inductor or current through the inductor has been changed, that means the inductor is supplying the energy to the minus VDC, or I can say inductor is releasing all that energy it has been storing the other time. That means actually let us say this terminal and this terminal, let us say this is terminal A and B. As long as the current entering into the terminal A, the inductor is said to be charging. But when the current starts leaving the terminal A, then the inductor is said to be discharging. So during time T2, the inductor is discharging. So if I try to plot the voltages and current for this duration, so for this duration from T1 to next for T2 duration, okay, this duration is how much? T2. Let us say this final time is T, or I can write T2 will be equal to time minus total time period minus T1. So I am applying how much voltage? Minus VDC voltage. But what is happening to the current? Current start decreasing because the battery is discharging, because the inductor is discharging. So for this time duration, the whatever the energy stored in the inductor or the current through the inductor starts going down and finally goes to 0. If the current waveform is like this, this is called as steady state condition of inductor. What do you mean by steady state condition of the inductor? When the inductor is subjected to different switching cycles. When the inductor is subjected to different switching cycles, that means once the inductor is connected to one polarity of voltage, once the inductor is acting like a discharging, or inductor itself is acting as a source. Once inductor is acting as a load, once inductor is acting like a source. This kind of two switching cycles are there means. So once in one cycle, the inductor is taking energy from the supply, and in another cycle, the inductor is releasing the energy to the supply or to the load, whatever it is, whatever is present. If the energy stored is equal to the energy dissipated or energy released, energy stored is equal to the energy released. See, where did the inductor current start from? 0. Again, where did it end? It ended 0. That means the universe is balanced, or I can say the operation of inductor is balanced. The inductor operation is balanced. Inductor operation is balanced. Or I can say the inductor is in steady state condition. Let us say what I am doing is I am allowing some time T2 for the inductor to discharge. Let us say I am reducing the value of T2. I am reducing the value of discharging time for the inductor. Let us say the inductor started discharging up to this much time only, and immediately I change the position of the switch to 1. Now again what happens? The inductor starts building up the energy. So it will build up energy to up some value. Again I place it at switch position 2. the inductor will discharge. Before it completely discharges, I will again put at 1 like this. So the inductor keeps on building up the energy or current. It never reaches steady state when you are not allowing it a certain amount of time to discharge all the energy. So then this kind of operation is called as unstable operation of inductor. So I can say that the inductor will remain in steady state when the energy before the starting of cycle should be equal to the at the end of the cycle, switching cycle. That is when the inductor is said to be in steady state, or I can say for the inductor to be in steady state from the inductor equation, which means VDC equal to L di by dt. From the inductor voltage current relation, I can write down the value of inductor current DIL is equal to 1 by L. So I will take the whole switching cycle from time period 0 to t. So t is nothing but the combination of period t1 plus t2 is equal to only the t. After performing the integration, I will get IL of t minus IL of 0 equal to, I will get this relation. For steady state operation of an inductor, what I told you, the current at the before the charging and current after the discharging should be the same. So if current before the charging means at IL is equal to IL at IL of 0, current after complete discharging is IL of t, isn't it? So this combination should be equal, means what will this term reduce to? This entire term will reduce to 0. This entire term will reduce to 0. If that entire term reduces to 0, then I can write VL into T will be equal to 0. Or I can also write this in other way, VL into T1 plus VL into T2 should be equal to 0. From this equation, I can also imply that the average voltage of an inductor VL average will be equal to 0, or I can say the inductor average voltage should be equal to 0. That is what the significance of this equation, isn't it? VL into T1 is the voltage building. VL into T1 is nothing but the voltage second in the time period T1, and VL into T2 is the volt second in time period T2. That should be equal to 0, means finally I am telling you that the average value of the voltage should be 0 for an inductor. When we talk about choppers, this T1 is nothing but the T on, T2 is nothing but the T off, and this VL, which is corresponding to T on, is the voltage of inductor during on state and voltage across the inductor during off state. So here it is the voltage into second, voltage into time. So this equation is also called as volt second balance theory, volt second balance equation, or this equation is also called as flux balance equation. Why is it called flux balance equation? Because the inductor will store energy in the form of magnetic flux. So magnetic flux built should be equal to the magnetic flux collapsed during the discharging of an inductor. So it is also called as a flux balance equation. So from this, I can describe the steady state operation of an inductor by using volt second balance equation or flux balance equation. From this, I will get a conclusion that for steady state operation of any inductor, the average voltage across the inductor should be 0. So under steady state, always the VL average will be equal to 0. VL average will be equal to 0. But you see here, the inductor is having that behavior of not allowing the changes in current. That means it always tries to maintain current stiff. Therefore, an inductor is also called as a current stiff element. What is it called as? Inductor is also called as a current stiff element. That means it always tries to maintain the current stiff. So one precaution that you have to take based on this property is that whenever you are using inductor in any circuit, you should make sure that the inductor will not be open circuited. Inductor should not be open circuited. If the inductor becomes open circuit or the circuit becomes open circuit, what happens to the current in the circuit? Current in the circuit will suddenly fall to 0. Current in the circuit will suddenly change in a very short duration of time, means what will be the voltage across the inductor? It will shoot up to some thousands of kilovolts. Then what happens? Whatever the switching device in that particular circuit, that switch will completely damage. So that care should be taken care while you are using an inductor. Because it is a current stiff element, it always tries to maintain current constant. Suppose you are suddenly open circuiting the circuit, then the inductor will try to maintain this current in the circuit by inducing a large voltage across the switch. This will lead to, if the rate of change of voltage is something less or high, then if the distance between the contacts of the switch is sufficiently high, or if there is sufficient dielectric strength between the switch contacts, there will be a small sparking across the switch, but otherwise the switch will completely damage. So while dealing with inductor, the circuit should not be suddenly open circuited. Okay, while dealing with inductor, the circuit should not be suddenly open circuited. So that is the behavior of inductor. So next we will deal the capacitor. So the same type of analysis applies for the capacitor also. As you know, a capacitor is such a device which will store the energy in the form of electrostatic field depending upon the voltage applied across the capacitor terminals, isn't it? That means the energy does not change immediately, means the voltage across the capacitor should not change immediately. That means capacitor is also called as a voltage stiff element. Voltage stiff element. So under what kind of switching conditions the voltage will suddenly change? Short circuit condition. If suddenly the capacitor is short circuited, what happens to the voltage across the capacitor? Will be zero. If voltage across the capacitor will be equal to zero, the current drawn by the capacitor is given by IC is equal to C dV by dt. If this rate of change is very sudden or suddenly you are short circuiting, then the current will draw a very huge amount of current from the source, or I can say it will short circuit the source or the supply mains. Capacitor will damage, any other connected loads to the source to the supply mains also will get damaged. So it is very dangerous while dealing with capacitor also. Circuit should not be suddenly short circuited where capacitor is placed. So that is a very, very important property of a capacitor. So similarly, as we have done for the inductor, for the capacitor to remain in steady state, so what is that quantity responsible for energy storage in the capacitor? Voltage at the beginning of the charging, okay, should be equal and opposite, or should be equal to the voltage at the end of the charging period, or I can say Vc of t minus Vc naught should be equal to 0, which can also be said would be 0. That means this term will be reduced to 0. So like we defined for an inductor, for a capacitor also we can define that current through the capacitor during on condition into on time plus current through the capacitor during off into off time should be equal to 0. So this is ampere and this is time. So this is also called as ampere second balance theory, balance equation, or this is also called as charge balance equation, because current into time is charge. So charge balance equation, that means the charge stored should be equal to the charge completely released. So these points may be again asked in some competitive exams also. He will tell that the steady state operation of a capacitor is described by which equation? Ampere second balance equations or volt second balance equations, or steady state operation of a inductor is described by which equations? Like that you may get questions. So it is very much important to note this behavior or to understand this behavior of capacitor and inductor, and then study the analysis of chopper or any other power electronic device. So based on this concept, I want to discuss another concept from this question, using this question which was asked in AP Transco AE 2019, a very recent question. So here is some source given and is asking you to find out what is the average power drawn from the voltage source. So there is a resistive load and this resistive load is drawing some power from the source. So here there is a voltage source and current source, is asking you what is the power drawn from this voltage source. So this current source has got no significance with respect to power, but it is indicating what is the current direction of that particular voltage source. So what is the voltage source? Voltage source, as per given in the picture, it is just a sinusoidal voltage source or AC voltage source. And what is this current source signifying? Current source is signifying that it is having a current in one direction only, like a DC. That is what the meaning of this current source figure. That means actually if that current source was not mentioned, because this is a AC circuit, current and voltage will follow the same sinusoidal form, but here according to what is given, now the current will be like a DC straight line. So this is the current waveform and this is the voltage waveform. What will be the average power drawn from the voltage source? So to find out what is the average power drawn, let us draw how the instantaneous power looks like. See, if you multiply voltage into current, then you will get the waveform of instantaneous power, something like this. You see, from this duration from 0 to pi, voltage is positive and current is positive, so the power is also positive, because power is equal to instantaneous voltage into instantaneous current. Similarly, from pi to 2 pi time period, voltage is negative but current is positive, so minus into plus is minus, so power is also negative. So if you want to find out what is the average power over one cycle, so average power over one cycle is a symmetrical waveform, so average power will be equal to 0. So the average power delivered by the source will be equal to 0. Now if you look at this particular source, this source is having one characteristic, that is its current is unchangeable, it's having a constant current waveform and voltage waveform is a variable. So I can also say this source is also called as a current stiff source. Like we were defining for L and C as current stiff load or current voltage stiff load. For example, let us say if there is an inductor. Inductor is what? Current stiff element. When you are using L as a load, it is also called as a current stiff load. Similarly, if you are having a capacitor, capacitor was called as a voltage stiff load. So the answer here would be anyhow B, 0 watts, because it is a current stiff source. Average voltage would be 0, because if you see average voltage is how much for a current stiff source, it will be equal to 0. So for a current stiff element or an inductor, what is the average voltage in the inductor? Average voltage in inductor for a current stiff inductor is 0. Understood? So like this we will get this relation. Suppose I am having a current stiff load, current stiff source. Current stiff source means it is that source where the current is a fixed current. Current waveform is a fixed one. Let us say I am connecting to a current stiff source. I am connecting a current stiff load like this. Current stiff load, I am connecting a current stiff load. So what will be the voltage across the load? So voltage across the load, which is an inductor, will be L di by dt. Because it is a current stiff source, the current will remain constant. That means di by dt will be 0. That means voltage will be equal to 0. That means the inductor is best replaced as a short circuit, or I can say the supply is getting short circuited, or I can say the supply is also getting overloaded. So this is a disadvantageous situation. So wherever you are having a source which is current stiff, the load cannot be current stiff. The load must be voltage. Likewise, if the source is a voltage stiff, then the load must be current stiff. So this combination has to be keep in mind. See, if this convection does not follow, then automatically the source gets overloaded. The source will get overloaded, and it is not good for the entire system. Okay, thank you for watching this video.